Hello and welcome back, fellow path integrators. Once again with an integral, a crazy looking integral full of trigonometric functions, full of sines and cosines. So how are we going to do it? We are going to start with reforming the integrand a little bit first. So what I want to do first is take a look at the denominator, because we could extract this cosine out of the brackets. So we would have like sine cubed of x plus cosine cubed of x could be written as as cosine cubed of x times sine cubed of x divided by cosine cubed of x plus 1. So we could write the whole term under the fraction. So in the denominator we could write it as cosine to the power of 6 times sine to the power of 3 of x divided by cosine cubed x plus 1 and the whole thing squared. Alright, so how can we use that now to simplify the whole integrand a little bit, to make it more, to bring it more into a form where we can substitute something? Well, what we're gonna do is we write the whole thing, the whole fraction, so it's like sine squared of x times cosine squared of x, the whole thing divided by cosine to the power of 6 times x, then times sine cubed, whereas we can actually substitute here, this is the tangents cubed of x plus 1 and the whole thing squared. Alright, so what we can do now is we can cancel some cosines out, so this will give us sine squared of x divided by cosine to the power of 4 of x times tangents cubed of x plus 1 and the whole thing squared. Alright, so what we're gonna do now is we're gonna bring one cosine squared, since this is cosine squared of x times cosine squared of x, we can bring one of that up to the sine and make a tangents squared out of that. So it will be like tangents squared of x divided by cosine squared of x times the tangents cubed of x plus 1 and the whole thing squared. Alright, what we're gonna do now is we have everything that we need to substitute now, and the best thing to substitute would be the bad color tangents. So what we're gonna do is we say, okay, our new substitution variable u is equal to the tangents of x. So what we do is we take the derivative of u with respect to x, which will give us 1 over cosine squared of x, and this leads to dx transforming as cosine squared of x times du. So now we can plug that into the integral. So our integral was in the beginning tangents squared of x divided by cosine squared of x times tangents cubed of x plus 1, the whole thing squared, and dx, and this is with a substitution now equal to u squared divided by u cubed plus 1 in brackets squared, and the cosines here, they equal each other out, so we are just left with this integral right here. And now we can do like another substitution. What we can do now is that we can say our new substitution variable z is equal to the whole term here inside of the brackets. So we say z is equal to, u to the power of 3 plus 1. So now we take the derivative dz with respect to du is 2u. So this leads us to du transforming as dz divided by 3u squared. I'm sorry, this is wrong, 3u squared. Alright, so now we plug that into our integral. So our integral has been u squared divided by u to the power of 3 plus 1 in brackets squared du. And now with our new variable z, we are getting 1 divided by z squared, the whole thing times 1 over 3 times dz. That's it. Now we solve this integral, which is rather easy, which is just minus 1/3 times 1 over z, and then we plug in what is z, which is u to the power of 3 plus 1, so we have minus 1/3 1 divided by u to the power of 3 plus 1, and to get our final solution we just have to plug in what u has been, and we substituted u with the tangents of x, so our final solution is 1/3 of 1 divided by tangents cubed of x plus 1. So I hope you liked solving this integral. If you want to see more of this content, subscribe to my channel, leave a like, and let me know in the comments what you would like to see next. Alright, bye!